And welcome back to the video. Today we're going to look at the Joule thief. How does it work? Why does it work? So, let's find out. This video is sponsored by PCBWay. Whether it's standard PCBs you want or advanced PCBs, or for that small, confined and well packed piece of kit, a flexi rigid to save on the wiring of the PCBs. They'll also do assembly, and if you don't want to do the assembly yourself, then you can order a stencil to do the surface mount yourself. And of course, once you got your board finished, you might want a box to put it in. And so they do CNC machining, sheet metal fabrication, 3D printing, or if you're going to sell a few, you might want to look at the injection molding and vacuum casting. So the next time you're doing something, don't forget, pop over to PCBWay and see what they can do for you. Well, how does a Joule thief work, you may ask? Well, basically it's a blocking oscillator forming a simple DC to DC converter. This type of circuit was first patented in about 1930s and only deemed to be called a Joule thief when someone stuck LEDs on it. So let's think about the circuit. When you first apply power to the circuit, the initial state of the transistor Q1 is off. Now the current starts to flow down through R1 and T1 secondary and into the base. And at some point Q1 will start to turn on. And as Q1 turns on, current will start to flow through T1's primary. T1 is configured so that as the current builds along with the magnetic fields, a current is generated in its secondary by the changing magnetic field. This current is in phase with the current already flowing through the secondary, so adding to it. This increase in base current turns Q1 on harder. This in turn increases the current flowing into its base due to positive feedback in T1. So Q1 is quickly driven into saturation. You could say it's generating a voltage in the transformer, but I find it easier to think in terms of adding or subtracting current into the base of the transistor, as I think it helps when thinking how the transistor's HFE plays a part in the circuit. The current keeps increasing, limited by the inductance of T1's primary, and at some point the current will stop increasing as the transistor collector reaches its point where it's limited by the HFE of the transistor and the base current. As the feedback base current is generated by the changing magnetic fields in the transformer, when this current stops increasing, the current generated in the secondary falls to zero. The current supplied to the base by R1 and T1 secondary is not enough to maintain the collector current, so the transistor starts to pinch off and limit the collector current flowing. Remembering that the collector current is the base current times the HFE of the transistor. With this limited base current, the current flowing in the collector starts to fall. The current falling in the primary, and thus the collapsing magnetic field, induce a current in the secondary that now opposes the current flowing into the base of T1, so it's driven off faster. But the inductor wants to maintain the status quo, so with the collapsing current in T1 secondary and its resultant energy that's stored in the magnetic field, it causes the voltage at Q1's collector to rise and try and maintain the current flow. This voltage will increase until it's high enough to cause D1 and D2 to conduct and light. And then when the magnetic field is finally collapsed to zero, D1 and D2 will turn off. Then the whole sequence repeats itself until power is removed or the input voltage falls to a point where the transistor can't operate. Our eyes can't see the fast flashing light due to persistence of vision, so the LEDs appear to be continuously lit. D1 and D2 have a secondary function of limiting the voltage on the collector to about 6 volts, twice the forward voltage of the LED, which is about 3 volts each. If the LEDs were not in the circuit, then the voltage would increase to the point where the transistor would fail due to exceeding its VCE limit, and that would be the end of your circuit. Now we'll see a quick build of the circuit with a little bit of background music. Right, here you can see a close-up of the transformer that I used. Just pointing at the yellow coloured wire, that's the original turns on the transformer. The red ones here are what I've added, about the same number of turns to make it into a transformer instead of a choke. Right, now we've built it, let's connect some power to it and see if it works. So the positive lead just goes onto the top, and there it goes, it's lit up. So it shows it's generating a voltage higher than 6 volts. Right, we'll bring the voltmeter in and we'll see what the supply voltage is. Taking a time to find the leads here. Right, here we go. I need some new crop clips. So we're running at about 1.4 volts. It's not mega bright because it's got quite a high value base resistor, and so you need to get it really bright, you need to have a bit more supply for it. But I wanted to see how little I could get away with, so I went for a reasonably high value of about 12k, I think it is, and it could be considerably lower. Most people say less than 10, but there you can see at 1.4 volts we're lighting 2 white LEDs, so at least 6 volts across them. Not that the meter will show you that, because it spikes and the meter's not fast enough, even on AC or DC. On DC it just shows you what the kind of steady state is. On AC it's just not fast enough. Well, we can turn the Joule fief into a pulse Joule fief with the simple addition of a capacitor across the base resistor shown here, and that slows down the charging and causes it to be paused in the off state for longer, but can cause other problems. And so what we follow on now is I'll show the circuit. I've added the 1000, actually I made it 1000 microfarad instead of 100 shown here, and we'll see how it went and how the flashing was picked up differently by 2 cameras looking at the same circuit. Now, I'd never noticed before, but the top-down view is with a Canon M50 Mark II, I think it is, and I'm changing different brightness levels, different lights on, and the one on the top right is my little microscope camera, and as you can see at this sort of flashing pulse rate with different light settings, the microscope camera is picking up flashing better. But even here you can see that with this lighting level it's missing some of the flashes, and some of these flash, one LED flashes and the other one doesn't. But the Canon, you can bet you don't see the flashes at all, it's completely missing it. And very strange, not sure why. Even make the picture a bit darker and the microscope, as you can see, is picking up every flash, and the Canon still not seemingly seeing them. It sees the odd one, and that must be something to do with the frame rate or something. But say, not being a camera buff, I'm not going to go into the Canon. I'm not going to go into the Canon and try and work out why it's not picking up every flash. So just thought I'd show you that out of interest, really. While recording this, I put that big 1000 microfarad cap across the resistor to really slow down the pulsing. What I found was, after it flashed, this sine wave, well not a sine wave, this pulse up there would appear and it wouldn't re-trigger, which was very strange. And if I moved the scope to that side, no noise, and if I moved it down to the base, and then it would trigger. Attaching the scope would cause it to trigger, and the signal would also appear on this side, and it would stay stable. So I thought, well, if I've got no noise on here, but I've got noise on the base. If I go back to the base, now it's flashed, and now I've got noise on here. So what I thought of doing is putting our 100 nanofarad, trying to use the scope to hold the two connections. It's very awkward here. I should have got a component with a longer leg. See, just touching it causes it to trigger. It's so sensitive. So that should oh no, that would have held them together, but it's pulled them apart. And now I bring it round, and what I want to do is get the crock clip to hold those two together. And if it's got it right, what we should find is it will flash but it won't burst into noise. I should be able to get the scope to trigger on that. So, edge, channel 1, see if we capture it. Yeah, screen has stopped working. I'm going to have to stop recording and sort that out. This will give you an idea of how good the Hameg scope is. Where's the scope? I pull it back a bit. Now, if I put it onto normal mode, so now it should capture it, and look, it's captured it on the scope anyway. And as you can see, it's capturing it each flash, but nothing on the program. And if I turn it off and put it on auto mode again, you'll see now the scope program is running. So how stupid is that? If I set it on the program mode, when that says auto, I'll switch it to normal on the scope program, because you can control it via, well, you're meant to be able to control it. Oh yeah, apply. Yes, so the scope has changed over to normal. And the scope is captured and the display hasn't. So if I stick it back to auto, the scope has gone back to auto and the screen is now capturing. So, pile of crap, excusing my French. But that was just to show you that by putting a decoupling capacitor across the two LEDs, 100 nanofarad, has killed that secondary oscillation and has brought the circuit back into doing what it was intended, of flashing. But the interesting thing, of course, to note is, I've also pointed out before, is that the microscope camera can detect the pulses, but does the Canon? Not every time. The Canon is very rare. If I up the voltage, also the frequency of the flashing will change. Anyway, that's about as far as I'm going to go on the how to slow down a Joule thief by putting a capacitor across it. Also seems to make the LEDs brighter when they pulse, but it looks like you might need a decoupling capacitor across the diodes to get rid of that funny oscillation that can happen. But again, the Joule thief is all this, if you change that inductor, it may not do it. That inductor was just made up of a choke that I found, and I just counted the turns and then put the same amount of turns on it. So nothing spectacular, it was just taken out the scrap box. So hope you find that interesting. One of the reasons for showing this is there was a chap on YouTube, or I can't remember the name of his channel. He'd built a Joule fief using 2 inductors, and here you can see I have 2 inductors, not a transformer. Now everywhere it shows you need a transformer because you've got to get the feedback, and this is the circuit. It's powered up. As you can see, there are no LEDs lit, and the inductors are sitting away from each other. Now when you looked at his circuit, he had definitely drawn it, I'll show you a link in a minute, a picture, or not a link, he's definitely drawn it as 2 separate inductors. I'll show you a drawing. I copied his drawing because I just wanted to prove to myself that it wouldn't work, but it does if you build it the way he did. So I've changed the base resistor. You need to get the base resistor much lower. I'm down to 1k now because I think the coupling's not so good, so a lower base resistor helps. Now what you'll find is if I get these 2 inductors and bring them together, you might see something happen. And he, when he mounted his board, put the inductors right next to each other, like resistors right next to each other, because he used axial ones and not radial ones like this. And this is just to show that when they're close enough together, the magnetic field is overlapping the 2 cores, and so they act as a transformer, and the closer you bring them together, the more it goes. And we're running at 0.9 of a volt at the moment. If I put the meter in and connect it up, 0.96 of a volt. And you can see, I'm trying to bring them together again. You can't read the meter now. I should have stuck one of these down so I can do it. Try and do it with one hand. So there we are. You're running 0.9 of a volt, and we're getting a lovely bright white LED, pulling about 3 milliamps. But lovely coupling there. If I rotate them, you'll see that, you know, rotating them when you're like that, there'll be no coupling whatsoever. So if you want to have inductors that don't couple on a circuit, you need to, if they're close together, you need to have them 90 degrees apart, because as soon as you put them into the point where they can couple, they will. So there is a Joule fief using 2 separate inductors and not a transformer, but having to keep them side by side so they couple. They'll also couple end on like that because the magnetic field is still going to flow. Now it's going to flow down through both coils, around, down through both coils and around, so it's still coupling lovely. So, you know, you could almost make this as a detector. As they come past, it lights up. Well, I hope you found that interesting enough, and hit the subscribe button, click on the like button, click on the notifications when you want to hear more, and well, sorry, when you want to see more, and I'll catch you on the next one.